Today we are going to learn about TSNE for cluster visualization, an expert guide. We will explore how to employ TSNE to effectively visualize clusters in complex datasets and enhance your data analysis skills.
Welcome to our expert guide on TSNE for cluster visualization. In this video, we'll dive into the world of cluster analysis using TSNE, or T-distributed stochastic neighbor embedding. This technique is pivotal in the field of data visualization, particularly when dealing with high-dimensional datasets. By the end of this guide, you'll have a comprehensive understanding of how TSNE can help you uncover patterns and insights in complex data. We'll cover everything from setting up TSNE for optimal visualization to integrating it with other clustering algorithms. Let's begin our journey into the fascinating world of data visualization with TSNE.
TSNE, or T-distributed stochastic neighbor embedding, is a machine learning algorithm used for dimensionality reduction. It is particularly effective for visualizing high-dimensional datasets by reducing them to 2 or 3 dimensions. This makes it easier to identify clusters or patterns that are not immediately apparent in the raw data. Unlike other dimensionality reduction techniques like PCA, TSNE is renowned for preserving local structures in data. This means it can maintain the proximity of points that are close together in the high-dimensional space, making it ideal for visualizing complex datasets. TSNE has found applications in various fields, from genomics to image recognition, where visualizing the groupings or clusters is essential for understanding the dataset. Its ability to reveal the underlying structure of data makes it a powerful tool for exploratory data analysis. As we delve deeper into this video, we'll explore how to leverage TSNE's capabilities to enhance your cluster visualization and data interpretation skills. Setting up TSNE properly is crucial for achieving optimal cluster visualization. The first step involves preprocessing your data. This often includes normalizing or standardizing the data to ensure that all features contribute equally to the distance computations. Next, you'll need to configure several key parameters in TSNE. One of the most important is perplexity, which affects the balance between local and global aspects of your data. A rule of thumb is to set perplexity between 5 and 50, but the optimal value can depend on the size and nature of your dataset. Another critical parameter is the learning rate, which controls how TSNE updates its embedding. A learning rate that is too small may lead to slow convergence, while one that is too large can cause the algorithm to diverge. Finally, the initialization of TSNE is random, meaning that different runs can produce different results. It's often a good idea to run TSNE multiple times with different initializations to ensure stable results. By understanding and configuring these parameters properly, you can significantly enhance the quality of your cluster visualizations.
The choice of distance metric plays a crucial role in the performance of TSNE. It determines how the algorithm perceives the similarity between data points. The most common metric used in TSNE is the Euclidean distance, which works well for many types of data. However, depending on the nature of your dataset, other metrics such as Manhattan, cosine, or correlation distance might be more appropriate. For instance, cosine distance is often used in text data where the angle between vectors is more meaningful than their magnitude. When selecting a distance metric, consider the characteristics of your data and what you want to achieve with your visualization. The distance metric affects how clusters are formed and can significantly impact the insights you derive from your data. It's beneficial to experiment with different metrics to see which one yields the most meaningful visualization for your specific dataset. Understanding the implications of your choice can lead to more accurate and insightful visualizations.
Enhancing cluster separation in TSNE involves fine-tuning various parameters to achieve clearer distinctions between clusters. Perplexity and learning rate, as previously mentioned, are two critical parameters. Balancing them effectively can lead to more distinct cluster separation. Another important parameter is the early exaggeration factor, which boosts the attractive forces between nearby points early in the optimization process. This helps in forming more pronounced initial clusters. Iterations also play a significant role. More iterations can help refine the clusters, but at the cost of increased computational time. It's essential to monitor the progress and adjust the parameters accordingly to find the right balance. Some practical strategies include gradually increasing the perplexity and learning rate and observing the changes in cluster separation. Remember, the goal is to achieve a visualization where clusters are distinct and meaningful. By mastering parameter tuning, you can leverage TSNE's full potential to enhance the clarity and insightfulness of your cluster visualizations.
Visualizing multidimensional clusters poses significant challenges due to the complexity and volume of the data involved. TSNE helps address these challenges by reducing the data to 2 or 3 dimensions, making it easier to visualize. While 2D visualizations are more straightforward and easier to interpret, 3D visualizations can provide additional depth and context, although they require more advanced tools and techniques to interpret effectively. When visualizing in 3D, interactive tools like Plotly or Matplotlib in Python can offer features that allow you to rotate and zoom into the clusters, providing a more comprehensive view. Interpreting these visualizations involves looking for patterns, such as the density and shape of clusters, and understanding what they imply about the dataset. The goal is to extract meaningful insights from the visual representation of the data. By effectively visualizing multidimensional clusters, you can gain a deeper understanding of your data and uncover hidden patterns that are not immediately apparent in higher dimensional spaces.
Integrating TSNE with other clustering algorithms can enhance the accuracy and interpretability of your cluster visualizations. TSNE excels at dimensionality reduction, while algorithms like k-means, dbScan, or hierarchical clustering are more suited for identifying and labeling clusters within a dataset. By first reducing the dimensions with TSNE and then applying a clustering algorithm, you can achieve more accurate and interpretable results. This combined approach leverages the strengths of both techniques, providing a more comprehensive understanding of the data. For instance, after visualizing the data with TSNE, k-means can be used to assign cluster labels, which can then be color-coded in the TSNE plot for better interpretation. Such integrations have been successfully applied in various fields, including genomics, image analysis, and market segmentation. By combining TSNE with clustering algorithms, you can not only improve the accuracy of your clusters but also gain a richer, more nuanced understanding of your data.
Interpreting cluster patterns in TSNE plots is an essential skill for data analysts. The shape and size of clusters can provide valuable insights into the dataset. For example, elongated clusters might indicate a gradient, while compact clusters suggest distinct groupings. The distances between clusters reveal the relationships between different data segments. Closely packed clusters might share similar characteristics, while distant ones could represent outliers or entirely different categories. Outliers, which appear as isolated points, can sometimes skew the interpretation and should be analyzed carefully. Practical examples of interpretation include analyzing customer segments in market research or identifying similar gene expressions in genomics. By understanding these patterns, you can extract meaningful insights and make data-driven decisions. Mastering the art of interpreting TSNE plots allows you to leverage the full potential of your data visualizations, leading to more informed and impactful analyses.
Exploring real-world case studies can provide valuable insights into how TSNE is applied across different industries. In the field of genomics, TSNE has been used to visualize gene expression data, helping researchers identify clusters of genes with similar functions or identify disease subtypes. In marketing, companies have leveraged TSNE to segment customers based on purchasing behavior, allowing for more targeted and effective marketing strategies. Despite its benefits, implementing TSNE in real-world scenarios often comes with challenges such as handling large datasets, ensuring computational efficiency, and interpreting complex visualizations. However, the success stories highlight how these challenges can be overcome, leading to impactful insights and better decision-making. By learning from these case studies, you can gain a deeper understanding of how to apply TSNE in your own work, enhancing your data analysis skills and contributing to more informed and strategic decisions. In conclusion, mastering TSNE for cluster visualization can significantly enhance your ability to analyze and interpret complex datasets. Throughout this video, we've explored the fundamental concepts of TSNE, from understanding its underlying principles to configuring it for optimal visualization. We've seen how parameter tuning can improve cluster separation and how integrating TSNE with other clustering algorithms can lead to more accurate and insightful results. Real-world case studies have highlighted the transformative impact of TSNE in various industries, demonstrating its value as a powerful tool for data analysis. As you move forward, continue to experiment with TSNE, refine your parameter settings, and explore its integration with other techniques. By doing so, you'll develop a deeper understanding of your data, leading to more informed and effective decision-making. Thank you for joining us in this expert guide to TSNE for cluster visualization.